Welcome to today's session on radiation, which is essentially your module 4. So in module 4, we are going to discuss the subsidiary laws. We have already discussed one subsidiary law, that is your Stephen-Boltzmann law. But here, as I said previously, that there are other subsidiary laws related to radiation, like your Planck's law, Wien's displacement law, and Kirchhoff's law. So all those laws we are going to discuss here, and then we are going to see also see something called as a view factor, and then eventually we will also go across or discuss something called as a radiation shielding, which is very essential with respect to practical scenarios. So when it comes to radiation, as I said, it is one of the mode of heat transfer, and it happens precisely because of electromagnetic waves. And that is why it does not require a medium. And as Stephen-Boltzmann law has said, that it depends on the absolute temperature of the body. So higher the temperature, more amount of radiation will be coming out of the body. Isn't it very like evident? So you see everything, as I said, the vibration or electromagnetic waves coming out from a body only stops if the temperature of the body is equals to absolute zero. But none of the object, including human body, or none of the objects surrounding it essentially is at absolute zero, or it cannot be taken to absolute zero even in a finite number of processes, that we know from the third law of thermodynamics. So definitely every body is emitting radiation, all right. But the thing is that when you go in front of a furnace or maybe an electric heater, all right, you feel even though like you are standing uh, quite a distant apart from the heater or the furnace, and you can feel this heat. Now there is no direct contact between the furnace and your body, so definitely it cannot be a conduction. And also, even though there is air between the two bodies, let's say the furnace wall and you, the convection is essentially uh, becomes more and more prominent if it is a forced convection. Otherwise, in natural convection, you don't feel the convective heat waves um, as strongly as in case of a forced convection. So definitely, if you are just standing in front of a furnace wall and if there are no fans or anything, then definitely convection is not the dominant mode of heat transfer. But here you are feeling a large amount of heat reaching your body every second, and that happens because of radiation. So as you can see, as the temperature of the body increases, the radiation will start creating burning sensation on your body. Even though like we are surrounded by objects which emits radiation, those are below a certain level, and that is why that does not create this burning sensation. All right. Whereas if you close very close to an electric heater and a furnace, you can feel that burning sensation because large amount of radiation, or to be more exact, large amount of thermal radiation is coming out from the body. Now, when it comes to radiation, it like all the electromagnetic waves, you can see it falls under this particular spectrum, and here on the leftmost side you will have your gamma ray. All right. After that, you get your X-ray. Then comes your ultraviolet. Then comes your visible range, that is VGR. Then comes your infrared. Then comes your microwave. And then comes your radio wave. So here we have highest frequency, lowest wavelength. So more penetrating power. Whereas if you see the radio waves, they have highest wavelength, okay, and lowest frequency. All right, so they have larger diffraction. That means if you want to send a signal and there's a mountain in front of you, then these waves can bend around the mountain and reach to the other side. That is why they are called as radio waves. So they can diffract very easily because of their high wavelength. But we are not bothered with the extreme end. Here we are more bothered with what is called as your thermal radiation. So it's essentially from here to here. And visible, this is called as a visible range. So visible range essentially starts from 0.1 micrometer to 100 micrometer. Okay. Now, when an object emits radiation, it emits radiation for all possible wavelength. And depending upon for which wavelength, how much radiation is coming out, that depends on at what temperature the body is. All those questions we will eventually answer with the subsidiary laws and see how exactly uh, a particular graph we will obtain. Remember one thing again, radiation spectrum. If we obtain for a body, we will see it as a continuous spectrum, which kind of reveals the fact that radiation is coming out for all possible wavelengths. All right. If it is a discrete spectrum, like your interference pattern and all these things, then or this one emission spectrum, uh, or whenever this electron jump will happen and then electron comes back down and then they reveal this spectrum. So those are your discrete spectrum. So only certain energy levels or certain wavelength is considered in those scenarios. So these are all about like 12th grade physics. I don't want to go into too much detail into those things. I probably have studied into the modern physics part of your 12th grade. So what I'm trying to start our discussion is that if you see Stephen Boltzmann law, okay, you see Stephen Boltzmann law, it says that Q dot by A flux is equals to sigma into T to the power 4, which is the absolute temperature of the room. Okay. Now, when you obtain a radiation spectrum, you usually will get a curve like this. Here on this side, you have your wavelength lambda, and this is called as your, on this side, we will have something called as an emissive power. That means how much radiation energy is coming out of that particular body at that particular temperature. So emissive power, we often denote it by E, is equals to sigma into A into T to the power 4. And in this particular expression, I would like to point out that this is the expression suitable only for emissive power of a black body. Now, what exactly is a black body? Black body is not supposedly has to be black in color. I mean, sun is a black body. It only thing is that it has to emit radiation of all possible wavelength, and whenever any radiation is incident upon it, it absorbs all the radiation incident upon it. Okay, so under those certain conditions, we can consider a body to be a black body. So in any practical scenario, you don't usually see a black body, only we do certain approximation. So under certain condition, we can consider a body to be black body because it's exhibiting a behavior very close to a black body, then we can assume it to be black body and do our calculation because it makes our job easier. Okay. So black body is essentially, it is a body which absorbs all the radiation incident upon it. Now, what exactly is the emissive power of a black body? Is essentially the area under the curve will give you the emissive power, or total hemispherical emissive power. That's what we want to call it. So area under the curve will give you total hemispherical emissive power. Denoted by E suffix B. Okay. And this is with respect to black body. You can also get with respect to a real surface also, but we will discuss the real surface a little later. Now, your Stephen Boltzmann law gives the value of total hemispherical emissive power. Why it is hemispherical? Because essentially radiation, when it leaves the surface, it leaves in the form of a hemisphere in all possible directions. Okay, it leaves in the form of a hemisphere in all possible directions. That is why we call it as a total hemispherical emissive power. Sorry, but I want, let's say I'm interested in how much radiation is coming out at a wavelength 4 micrometer. How can I find that? Because Stephen Boltzmann law does not answer that. He just says what will be the total energy output from the surface. But at one particular wavelength, how much energy is coming out? How would I know that? In respect to this one, we can have something called as a Planck's law. Okay. So in case of Planck's law, what we are trying to find out is called as a spectral emissive power, where the spectral means it is related to wavelength. For any particular wavelength, what will be the so Planck gave an expression So B means black body, and when you write lambda, that means it's with respect to a particular wavelength. So it's a function of lambda and t. Whereas if you see the expression for given by Stephen Boltzmann law, it's only a function of t, not a function of lambda. So this can be written as C1, which is a constant, lambda to the power 5, and then exp means exponent, C2 divided by lambda into t minus 1. Okay, and the unit definitely this will be watt per meter square, and since we are dealing with wavelength per unit wavelength, so we are going to find it with respect to micrometer per unit micrometer. Here C1 is given by 2 pi. These are all constant. Here this is Planck's constant. Don't get confused with heat transfer coefficient. And C naught is the velocity of light, C naught square, and it comes around 3.742 into 10 raised to 8 watts micrometer, sorry, to the power 4 per meter square. And C2 is HC naught, again here uh, this H and C naught are Planck's constant. One point 439, as far as I can recall, into 10 raised to 4, or 1.5 also you can take, not an issue, micrometer Kelvin. So if you integrate, the good thing about this is this Stephen Boltzmann law and Planck's law, they kind of prove each other. So if you just integrate Planck's law for all possible wavelengths, so wavelength starting from 0 till infinity, and if you integrate it, d lambda into d lambda for one particular wavelength. What I'm trying to say is that, see, if I have sorry for the interruption. You see, if we have like total emissive power you want to find, then this is area under this particular curve. So in this particular curve, I will choose one particular wavelength range. Let's call this as d lambda, and the area of this one will be, let's say the value for spectral emissive power is eb lambda. Then the area of this one will be means this small strip will be ev lambda into d lambda, and then we have to integrate it from 0 to infinity. So wavelength stretches from 0 to infinity. Eventually you will get that if we do the integration, we will end up getting here a is not there because per meter square we are doing into t to the power 4. This is the expression we are going to get. So Planck's law kind of proves the existence of Stephen Boltzmann law also. With the help of each other, we can understand it. So for one particular wavelength, we can find, or which is called as a spectral emissive power, with the help of Planck's law. I leave this integration up to you. You can perform it. I'll let it be a kind of an exercise for you. Next one that we need to understand is one more subsidiary law, which is called as a Wien's law. Now, Wien's law is a very interesting law because when we have like it's based upon practical observation. See, very interesting fact that we can see with respect to this emissive power curve, or with this radiation curve, is that I will start with very small temperature. All right, the curve will be something like this. Okay, only a black body will stretch from this end to this end. For any real surface, essentially it will be a small portion where the wavelength will be coming on, graph will be coming on. Then let's say this is with respect to temperature T1. Okay, now as we start increasing the temperature of the body, definitely the area of the curve has to increase, because now more amount of radiation is leaving the surface. So then we go with this one, we will see a curve something like this. It won't be too exact, exactly how we usually get the curve. Just please forgive my poor penmanship. Then if we keep on increasing, I will get a curve like this. All right. If we increase it even further, we get a curve like this. Sorry. So you see here, in the first case, let's say this is T3 and this is T4. And definitely T4 is greater than T3 is greater than T2 is greater than T1. So slowly we are increasing the temperature of the body. So initially you see this is the wavelength for which maximum amount of radiation is coming. Every other wavelength has lesser amount of radiation. Only this particular wavelength has the maximum amount of radiation. Similarly, the next point in the curve will come like this. Similarly, the next point in the curve will come like this. And the next point, maximum point will come. So as you can see, as we are increasing the temperature of the body, the wavelength at which the maximum radiation is coming is shifting towards a shorter wavelength. Okay, that is why a large amount of ultraviolet radiation also comes with respect to sun's radiation, because sun's temperature is very high. All right. The interesting fact is that if you obtain a proper graph, then all this point, sorry, will fall in a straight line. And this is what Wein's displacement law tells you. So Wein's displacement law essentially finds out the equation of the straight line, which is lambda into t is equals to, or we can lambda into t, we can call it to be max, only for maximum radiation scenario. Okay, it will be 2897.8 micrometer Kelvin. So if you just know what is the temperature of the body, let's say T equals to 500 Kelvin. So you just substitute in this equation and you will know the wavelength for which maximum radiation is coming out. Okay. Now this particular graph also clearly illustrates one thing, why tungsten filament bulbs went out of business. Okay. Now tungsten filament will be usually heated to a very high temperature uh, to produce sunlight. So whenever we are going to a very high temperature, we see, different color, we will see that only a small portion of the radiation, to be exact 25% of the radiation falls under visible range. Okay, remaining 75% are other radiation. But when you are using a bulb, what is your primary purpose? Your primary purpose is to produce radiation of visible range. So in tungsten filament, we are wasting 25%, sorry, 75% of the energy in producing other radiation, and only 25% of the radiation is useful to us. So that is why those were highly inefficient modes of illumination. That is why eventually they replaced it by CFL bulbs. Okay, so this is all about waste displacement law. Next subsidiary law that we need to discuss is your Kirchhoff's law. But before we go into Kirchhoff's law, let us discuss some of the radiation properties. So we're talking with radiation properties. The first radiation property that we are going to discuss is emissivity. It's usually denoted by epsilon, and it is radiation emitted by the any real surface compared to radiation emitted by black surface at the same temperature. Remember, this is a very crucial point. So if somebody asks you what is the definition of emissivity, don't forget to mention that it's a ratio of emissive power of a real surface with respect to emissive power of a black surface at the same temperature. Because if the black surface is at higher temperature of the, or the real surface is at a higher temperature compared to the black surface, then definitely numerator will be higher than the denominator, and emissivity value will go greater than 1. But that will be wrong, because if you see, comparison has to be on a similar ground. So a black body will emit radiation like this, which will be represent area under the curve will be represented by EB, and whereas a real surface will emit radiation like this, or the curve we will get is for the real surface. So definitely you can see the area under this blue curve is definitely less than the EB, provided both the bodies are at the same temperature. Otherwise this can exceed. Okay, so now this is your definition of emissivity. Next is your absorptivity. And before absorptivity, I mean, like along with absorptivity, we will try to define some other radiation properties. So what are those? Let's see. So first, say whenever a real surface, this is a real surface, whenever a real surface interacts with the radiation, usually three things happen. So this is your incident radiation. All right. Now a part of the radiation will be absorbed, a part may be get reflected, and a part may get transmitted if the body is not opaque. Okay, so let's say I have a body which has matte black finish, and another surface which has a shiny black finish. Then in this case, absorptivity will be more, reflectivity will be less, whereas in this case, shiny black surface, absorptivity will be less, reflectivity will be more. I mean, or you can make a direct comparison between these two. Absorptivity in a matte black finish will be more compared to shiny black finish, and reflectivity will be less in matte black finish compared to a shiny black surface. Okay. So how do we define? So absorptivity is defined as alpha okay. Reflectivity rho, transmittivity as tau. So this is amount of radiation absorbed, amount absorbed by amount incident. Okay, this one is reflected by incident, and next one is transmitted by incident. Right. Now when an incident radiation comes, it will be either absorbed, reflected, and transmitted, and all of this together will be your incident radiation. Now if I divide both left side and right side of this equation with incident radiation value, then this will be amount of radiation absorbed divided by I plus IR by I plus IT by I, and this will be equals to 1. This is your absorptivity alpha, this rho tau equals to 1. These are the radiation properties or the relationship between them. Okay. Next thing, sorry. That's no problem. Okay. Now, since we now know the radiation properties, we can have a discussion related to Kirchhoff's law. In Kirchhoff's law, it essentially tells you that a good absorber is also a good emitter. So you can pretty much notice it. that if you, let's say I make a pot of coffee, and then I put the coffee in two different glasses. One is made up of stainless steel, another is made up of ceramic. You will see that the stainless steel glass will heat up extremely fast, and so fast that you cannot even hold that particular glass anymore. But the ceramic cup, you can easily lift it up. Why? Because ceramic cups are bad conductor of heat, and that is why it will heat up slowly. One more thing that you can notice is that if you keep both of this cup to open environment, you will see that after same amount of time has passed, the stainless steel cup will be much more cooler compared to the ceramic cup. That is, since it's a good conductor of heat, it will give up the heat much at a faster rate compared to a ceramic cup. The same thing was noticed by Kirchhoff, and he said that a good absorber will also be a good emitter. During summertime, when most of us have reinforced concrete houses, and those houses, since they are made up of bricks and cement, they are bad conductor of heat, and that is why during the daytime it will keep on absorbing heat, and then from the evening time it will start to reject this heat, and that is why in these RCC houses the room will stay heated up even up till 11 o'clock or 12 o'clock uh, night time. This is precisely the reason. Since they are bad conductor of heat, they will absorb the heat slowly and they will reject the heat also very slowly. So Kirchhoff's law directly says that absorptivity and emissivity will be same for a black body essentially. This is also known because emissivity value will be equals to 1 for a black body, and absorptivity value will also be equals to 1 because a black body essentially absorbs all the radiation incident upon it. So these are all about all the subsidiary laws. We will start our discussion with something called as a view factor and solid angle in the next session. Thank you.